Hello and welcome to this manufacturing systems technology part 2 module 13. In the last module we had learned in details about the failure mode effect analysis and tried to take a realistic situation in an automotive paint shop and try to do an FMEA based on the realistic nature of the problem on the line which is concerned with the operators and the supervisors of the particular area. Today we are going to sort of look ahead and see into a little more into what are the different tools and how do you record quality or how do you document quality. So there are about 7 tools which exist in this area, which are also known as the 7 tools of quality control, and they include the histogram, the check sheet, the Pareto chart, and this is all really a statistical good representation of the whole quality problem, so that you can at a glance take a stock of the situation and see what are the improvements that the situation would need, so that there is a final goal of high quality product achieved. You have Pareto charts, cause and effect diagrams, defect concentration diagrams, scatter diagrams and control charts. So I am going to look into the individual aspects of all these different systems and give you an idea of what really the purpose of all these different tools are. So let us start with the histogram. So the histogram is again a statistical way of representing the frequency of occurrence of a certain product or a certain product specification in a production system. For example, if the production system were a NC lathe and you were controlling or you are trying to sort of produce circular shafts or cylindrical shafts by turning process on these NC lathe systems, so that the shaft would have a diameter or recorded diameter of 1 plus minus 0.05 inches. Okay. So really it would be about starting from 0.95 inches all the way to about 1.05 inches. So when we want to measure what is the process control at this particular NC system, we would need to do measurements, number 1, and number 2 is record the measurements in an organized way, so that you can have some kind of a frequency distribution. So I think this had been covered in the last module, that the frequency versus the particular shaft diameter measurement is represented in this particular way, and we were talking about 300 plus samples which we were representing for the various shaft diameters, and this way it would provide you a sort of central tendency of this distribution of the total amount of measurements which have been done, and the central tendency in this case, as you can see, is about 1 inches, okay, which is the correct central tendency. So if there is a deviation in the central tendency or even the spread of this distribution, the spread being how far away from the mean is really the the two ends of the whole spectrum of the shaft diameters, then you need a process control. Okay. So that is how you represent in a histogram the different dimensions. Let us also look at check sheets. So check sheets are a very important tool in production control. On a regular basis you need to fill up these check sheets. In fact, in an automotive shop there is a check sheet with every vehicle, and there is an inspection done at a level of almost a 0 defect, where whatever defect has come out because of the process or the component would have to be corrected before the final vehicle is made assembly okay. Okay, so that is how the vehicle shops actually go. So in this particular way, in this particular tool, the check sheet, it serves as a useful tool for collecting historical or current operating data for process under investigation. I just mentioned about the automotive shops. So in assembly shop, a check sheet is really the mother of all history of the production of the vehicle. This is recorded in terms of the chassis number and the engine number, and in fact this is retained for a period of almost one lifetime of the vehicle, so that if supposing there is some warranty failure issue which comes up, you can refer to this check sheet and see if there was a repair done on the particular vehicle, or even to an extent of sometimes using that data towards recalling some of the vehicles which may have potential problems of a certain batch of component being fitted. You must have heard a lot of times about Toyota pulling out its vehicles which have been supplied, or even some of the other major auto manufacturers sometimes putting an embargo on some chassis number, cut off chassis numbers, and then trying to recall that back from the customer because something went unescaped where they feel there may be a potential threat to the safety of the customer. So these kind of tracking back of a production event which has happened way back, maybe 2 years back or 1.5 years back, can be possible because of the check sheet. So let us look at how the check sheet can be made. It is a sort of a recording of the causes of failure of a system or product performance, and this can be due to a number of defects within the particular product that we are talking about, and it may not even affect the product performance, but certainly affects the quality of the product. So a common example, for example, are the spark plugs, okay, and so there may be various defects in this spark plug, like for example dirty cores, raised studs, off center wire, mixed plugs, bad plating, chipped cores, dirty insulators, poor gapping, cement on core. So if somebody is associated with the automotive industry, he will sort of realize this in a little bit better manner, is due to the raised studs. And in a spark plug, really if you look at the overall tip of a spark plug, something in this particular manner is what the overall design of the tip of the spark plug is. And in fact in this particular spark plug there is some kind of a ceramic insulator, and then there are electrodes which are typically metal electrodes. And when they are talking about the problem of the raised studs, they must be referring to a situation when the gap between the electrodes is uncontrollable because of the way that the stud is embedded into this ceramic outer or the ceramic insulation housing which has been shown here, okay. So that's what raised studs means. For example, you can have mixed plugs, there may be 2 or more variants of these plugs going into 2 different vehicles, and there is a possibility that these plugs get mixed up while getting packed into their packages or their boxes, which would be used for transporting this to the from the vendor end to the assembly unit. So there may be also problems related to the cores. The cores can be dirty. The cores are basically the ceramic cores that we are talking about here. They can be dirty, they can be also probably chipped, so there may be some possibility that the ceramic housing is, because of the handling issues etc., they may be broken at certain places and chipped at certain places. There can also be a poor gapping, that means the gap control here as you are seeing between the electrodes may be not appropriately sort of produced, or then there can be some kind of cementing on the core. There are many sort of adhesive cements which are used for putting together the core of the particular spark plug, so that can be one of the reasons. So all these different aspects are the different type of defects which are produced while manufacturing these spark plugs. And what the purpose of a check sheet is really to record that on a daily basis. For example, if there is some production, how many of these defects are getting generated if it is 100% inspection. So supposing there is a final inspection person related to the spark plug who is actually looking into the quality of these plugs, he would actually try to tally and record the number of occurrences of a certain particular kind of defect, and he is trained to look at this plug and tell what defect really the plug has. And so he has actually on the day one recorded, for example, 500 dirty cores, 1100 raised studs, 140 cases of off centered wires, about 450 mixed plugs, and then about 800 of bad plating, and then obviously 125 of poor gapping. So in total, out of whatever number of spark plugs have been produced on a given day, he has recorded about 3115 defects of different kinds. So basically now you are clubbing together the defects of certain types, and these are, mind you, the defects which are the most concerning ones from the fitment point of view, and that is how a whole check sheet is designed. Okay, so the purpose of the check sheet is really to record statistically what is the frequency of occurrence of a certain particular defect in a tabular manner, which you were earlier doing in the histogram manner, in probably a graphical way or in a bar chart of representation. So similarly you have similar kind of defects recorded in day 2, day 3, 4 and 5, and you may be seeing that on certain days there is some kind of a pattern here that the raised studs are typically there on day 1 and this most on day 1 probably, and then on day 4 to some extent, and then day 5 to some other extent. Okay. So probably this stud defect is because either it is towards the end of the tool change or the beginning of the tool change which is causing this, and probably around this region, let us say. So therefore obviously from this check sheet one can interpret that on day 2 and day 3 there are no raised studs. Probably the machine which is used to pinch the stud and place the stud into the ceramic core may be behaving in a proper manner during day 2 and day 3, and probably there is some kind of a changeover between 3 and 4 which causes again some kind of a defect on day 4, which increases because of some deviation within the machinery on day 5. So obviously this is one of the areas where you have to do some quality improvement related to the machine, maybe some foolproofing, so that this raised stud defect does not come in the spark plug. You can also look at the fact that dirty cores in fact are recorded as a defect every day, and this is probably more of a control issue from the supplier end, because the cores are supplied obviously by another vendor, and the assembly of the spark plug is from the bought cores from that particular vendor along with the different other components. So therefore this is related to mostly a supply issue, and you can control the quality of supply by either a vendor changeover or doing a process audit at the vendor end, so that the dirty cores can actually be reduced. You can also see various other issues, like let us say things related to off center wire or mixed plugs, bad plating, poor gapping on the day 1st, whereas some of these defects do not get recorded on day 2 and 3. One of the interpretations could be that the concerned person who is doing the inspection on let us say a particular day of the week, he may be oversensitive to recording of the quality, and that is why some of the defects which are otherwise not recorded on day 2 and day 3 are getting recorded on day 1. So various interpretations can be possible from this check sheet, and then before taking or planning a countermeasure one has to really look into the process of the inspection to sort of ascertain whether the inspection is done on a equal basis on all the days, or is there a parity between day 1, day 2, day 3, day 4 and day 5 of the inspections. However, it is very important to gather together this data on a regular basis, because this gives you a lot of history about how the particular component is being produced and what can be the process control, so that the quality of the component can be within the control limits. So that is the check sheet. Let us now talk about the Pareto chart or the Pareto analysis. So basically it is about identification of the most important or most repetitive or high occurrence defects which need to be controlled in a process to have overall quality control. So typically a Pareto diagram is also like a bar chart. Let us say for example if these 9 defects, for example what you recorded in the check sheets earlier, like dirty cores, mixed plugs, raised plugs, bad plating, chipped cores, off centered wires, dirty insulators, poor gapping and cement on core, these all 9 defects are recorded now in terms of the frequency across one particular week, 5 days of a week, and you can see that they are about close to 35% of D1 and about 20% of D2, and then about close to 11 or 12% of D3, so on and so forth. So you are basically recording defect wise frequency of occurrence as a percentage out of 100, and then the idea is that once you have recorded this, you can identify what are the first 3 defects of topmost priority which has to be focused before you can so in order to solve the quality problem. Okay, so it gives you a sort of prioritization as to what has to be focused first to eliminate, so that the overall level can come down to a reasonable level, and then you can actually see if you want a 0 defect you can go to the lower ones later on. So it is basically the first priority of the problems which need to be tackled that the Pareto chart illustrates. So you can actually have a good basis of Pareto plotting from the check sheet, where all these different defects are recorded in different manner. You also have a cause and effect diagram. It is also known as the fishbone diagram or the Ishikawa diagram. This is a very important tool towards understanding the cause and effect relationship between a quality problem to happen and the causes therein which would cause this problem to happen. So typically you have 4 different aspects which you talk about here. Let us say when we are talking about a shaft being turned on a NC system. So the concern here really is the quality of the turned part or quality of the shaft which has been passed through the NC turning process, and there may be many issues related to the turned part. So typically you call it the 4M, the man, material, machine and method. That is how you describe this Pareto analysis, this cause and effect analysis or a fishbone diagram. So here for example if you look at man is basically the operator, okay. So all things related to the operator skill or the level of control that the operator has, does he do inspection from time to time of the output that is coming out of the system, is basically a part of the human skill, or we can call it grouped under the man cause. The machining conditions and the the tool conditions as well as the machine tool, these all different aspects are really related to the turning process. So if you look at, let us say, the machining conditions, for example, is the feed correct, is the depth of cut not varying, is the cutting speed also not highly variant. These are some of the things you should investigate for mentioning the quality of the turned part. For the material, in particularly the tool condition, the insert condition, whether the material is appropriate, is it hard enough to sort of plow on the workpiece and trying to create a turned component, or does it need regrinding so that the blunt tool can be again sharpened back and the material removal can be faster or in a more accurate or predictable manner. These are related to the material side. And then obviously this is the method side, which may include a lot of systems or aspects. For example, is there a machine chatter, okay, in the overall method which is creating a for example a wobbling of the turned part, which may result in some kind of a poor surface finish. We can also talk about whether the process capability of the system is poor, is it really producing a mean distribution of the outgoing quality which is deviated from the specification mean, or maybe is the process an outlier completely from the specification which has been given, or is the machine really ready to support the specification. Can it have a sigma which is tight enough, can it have a deviation which is tight enough so that it can lie within the specification. So these are the issues which you address in the methods area, and then the methods can also have some noise factors like the humidity control, the temperature control, which is the environment control, or even let us say or even the sub part of the material area, which may include the workpiece material, the quality of that material or the composition of the material that you are machining, etc. So in fact briefly speaking, you have divided these whole variable factors which would cause this quality problem in the turned part into a man related, which is this operator line here, material related, which can be related to the tool condition and the workpiece condition, machine related, which is really related to the machine tool conditions, and then the method related, which may include the machining conditions as well as the environmental conditions, which are noise factors. So in fact all process defects can be recorded as the Ishikawa diagram or the this kind of a fishbone diagram, and this is credited to Dr. Kaoru Ishikawa, who actually was the inceptor for this kind of a concept. And so if you have several such fishbone diagrams illustrating your quality of the part, it is really a very organized study as to what would be the causes and what would be the effect. So once it has been distributed as a cause and effect, you can sort of try to do process improvements, or improvements in the methods, or improvements in the let us say the man related training aspects, etc., or even the materials, so that overall the quality problem gets sorted out because of these addressing of the various issues which cause a non-compliance of the quality of a particular product or a part. So that is how you can analyze the cause and effect. So in fact we have recorded the histogram, the Pareto analysis, the check sheet analysis, and the cause and effect diagram. So 4 important tools of QC. We will again revisit this problem in the next module, when we will actually try to lay out the other 3 which are equally important for studying of the quality control function. So as of now we would like to end this module. Thank you.